Hello, friends. Jim here. Interesting article appeared on the online publication EOS. Ocean deserts could help capture CO2 and mitigate global warming. Various nutrient sources in the upper waters of oceanic subtropical gyres, which are the Earth's largest oligotrophic ecosystems, play a crucial role in governing the sequestration of atmospheric CO2. Now, the paper has quite a few co-authors on it. It was just published on the 1st of December 2023. I will get back to this figure in a bit. There's a lot going on here in this figure. Subtropical gyres are basin-wide currents that form vast ocean deserts covering between 26 and 29% of the world's surface ocean and impact the supply and movement of nutrients. While there have been some major advances over the past few decades, our understanding of these gyres is still limited. A recent study in Reviews of Geophysics presents a comprehensive data analysis of subtropical gyres in the North Pacific. We asked the authors to give an overview of subtropical gyres, how scientists study them, and what questions remain. So what I want to do now is, before we get into this basically Q&A that follows, is let's take a look at the abstract of this paper. So here is the abstract. Upper ocean biogeochemistry of the oligotrophic North Pacific subtropical gyre, from nutrient sources to carbon export. Okay, bit of a mouthful, but pretty much straightforward what they're talking about. And once again, we see the statement, subtropical gyres cover 26 to 29% of the world's surface ocean, are conventionally regarded as ocean deserts due to their permanent stratification, depleted surface nutrients, and low biological productivity. I will explain briefly why that is. Despite tremendous advances over the past 3 decades, particularly through the Hawaii Ocean Time Series and the Bermuda Atlantic Time Series study, which have revolutionized our understanding of the biogeochemistry and oligotrophic marine ecosystems, the gyres remain understudied. We review current understanding of upper ocean biogeochemistry in the North Pacific subtropical gyre, considering other subtropical gyres for comparison. We focus our synthesis on spatial variability, which shows larger than expected dynamic ranges of properties such as nutrient concentrations, rates of nitrogen fixation, and biological production. This review provides new insights into how nutrient sources drive community structure and export in upper subtropical gyres. We examine the euphotic zone, they label it here as EZ, in subtropical gyres as a 2-layered, vertically structured system. A nutrient-depleted layer above the top of the nutricline in the well-lit upper ocean, and a nutrient-replete layer below in the dimly lit waters. These layers vary in nutrient supply and stoichiometries and physical forcing, promoting differences in community structure and food webs with direct impact on the magnitude and composition of export production. We evaluate long-term variations in key biogeochemical parameters in both of these euphotic zone layers. Finally, we identify major knowledge gaps and research challenges in these vast and unique systems, so you can keep funding us to do future studies. First of all, let's define what's meant by oligotrophic. Okay, we see this word right here, oligotrophic. Oligotrophic simply means nutrient poor, low biological productivity. Contrast that with eutrophic, which is high nutrients, high productivity. To a point, we've all heard of eutrophication, which is when you throw in too much nutrients, and then you have the algae, the primary producers going crazy, and then they basically deplete the oxygen. You get increased biological oxygen demand, which can lead to fish die-off. Because don't forget, producers also respire. When they're not photosynthesizing, they're using up the oxygen. So if you got too many of the phytos or the algae, they're going to draw down the oxygen in the water. So that's what's meant by oligotrophic. Now, they define a well-lit upper ocean that is low in nutrients, and then nutrient replete layer below in the dimly lit waters. Well, all depends where is that stratification occurring. If the stratification is right where this goes from well lit to not so well lit, to dimly lit, then you're not going to be able to get the nutrients into the well lit layer. If the pycnocline, right, the stratified layer, if the pycnocline is at the bottom of the dimly lit waters, then you could have, for example, wind forcing that does some vertical mixing in this layer, both layers, the well-lit and the dimly lit, such that you can bring up nutrients in a dimly lit layer into the better lit layers. So we have to look at the physics as to, what is driving that as well. Okay, key points. Subtropical gyres display larger spatiotemporal dynamics in biogeochemical properties than previously considered. And an improved two-layer framework is proposed for study of nutrient-driven, biologically mediated carbon export in the euphotic zone. Okay. So the plain language summary. Vast subtropical oceans feature basin-wide anticyclonic gyres. Basically, an anticyclonic gyres has a convergence zone in the middle, okay, which restrict vertical supplies of nutrients, resulting in low surface nutrient concentrations and generally low rates of bioproduction. Most of the ocean is biological desert. Where you get the productivity, the great majority of oceanic productivity, is coastal regions. And especially where you have Ekman pumping or an upwelling with Ekman pumping, bringing the nutrients onto the shelf. That's where you get your productivity. Look where some of your high fishing grounds are. Georges Bank, Grand Banks. Well, those are pretty close to the shore. We're not too far offshore, but they're over the shelf. And you bring in nutrients. Look at the upwelling, for the anchovy fisheries off the western coast of South America. When it would crash, that was due to El Nino, because it happened around Christmas time, with the thermocline / pycnocline being depressed, going further, deeper in the water, and no nutrients coming up, no upwelling. On the same token, of course, yes, you need stratification to lock the nutrients in so that and keep the phytoplankton in the photic zone so that they can do their thing. But without the breakdown of the stratification to allow the mixing, to allow the nutrients to be brought back up into the shallow lit layers, that stratification does not break down, the nutrients eventually get used up, and then the primary productivity drops off. And we're seeing this. Because of all the heat, the stratification is starting to intensify, as well as the marine heat zones and so forth. So let's see. So what else? So we through a comprehensive data reanalysis. I need to go back up here. Subtropical gyres have therefore traditionally been regarded as ocean deserts. Through a comprehensive data reanalysis focusing on the NPSG, we find larger than expected spatiotemporal variability in biogeochemical properties in subtropical gyres, including the distribution of nutrients, nitrogen fixation, biological production. Such variations are most pronounced through the sunlit water columns, the photozone, including sharp gradients in nutrient concentrations and sources and microbial community structure. Based on analysis and synthesis conducted in the study, we show evidence for the functioning of a two-layer euphotic zone habitat, with each layer differentiated primarily by inputs of sunlight and nutrients. Our understanding of long-term biogeochemical variability is relatively restricted owing to a lack of reliable long-term observations at adequate spatial scales. And they suggest, more research needs to take place. So that's the abstract for this paper. Behind a paywall, by the way, like an expensive paywall. I tried to access like $50. So, yeah. So let's go back here. And first of all, I want to, give you an idea overall of the oceans. So this is, a schematic gives you an idea of the major currents that take place on the surface of the oceans. The bold-faced letters are the gyres. So this is the North Pacific subtropical gyre, South Pacific subtropical gyre. And if you look at this, you got the North Pacific current, the California current, the NEC is the North Equatorial current, and then the Kuroshio current. So if you look at this, it makes a nice little loopy-doopy. There's your gyre. Okay? And the South Pacific Southern Gyre, you have the South Equatorial current, right? East Australia current, South Pacific current, and then the Peruvian coastal current. And notice it goes this way. So this one flows clockwise. This one flows counterclockwise. But what happens is, due to Coriolis, the deflection is to the right in the northern hemisphere. So water gets pushed this way, gets pushed this way, gets pushed this way, so that the water piles up in the middle, it converges, and you have a downwelling. Downwellings bring stuff out of the photic zone. And it's also a basis for the biological, or is one of the mechanisms for the biological pump that allows sequestration of stuff to great depths. Now, considering the southern Pacific subtropical gyre, deflection is to the left in the southern hemisphere due to Coriolis. So you're still going to get a convergence zone with the downwelling in the middle. We have the North Atlantic subtropical gyre, South Atlantic subtropical gyre, Indian Ocean subtropical gyre. Now, if you look here, it says the NECC, that's the North Equatorial Countercurrent, and it pretty much follows the equator. But as you can see, it is in a flow opposite direction, west to east, and in between the north and south equatorial currents that flow east to west. Here's the Gulf Stream, Labrador Current, East Greenland Current, right? North Atlantic Current. There's also the North Atlantic Drift that goes this way. The return flow, and again, the same thing, NEC, NECC, SEC. And this, of course, is the Antarctic Circumpolar Current. Kind of loops around there. So that's an orientation. And the Kuroshio, by the way, goes a little further north here, I guess, printing space. It actually comes up to about here. A branch goes off into the Arctic Ocean through the Bering, bringing some ocean heat with it, yada, yada. Now, what's interesting, you have here the Alaska current here. There's actually a gyre that forms in the Gulf of Alaska, and it is cyclonic. In other words, it is counterclockwise in the northern hemisphere, which means the flow is to the right, so it's away from the gyre. It creates a divergent zone in the middle and an upwelling in the middle, which, wait for it, brings nutrients. That's why the Gulf of Alaska is rich it has a rich fisheries. Physics drives the biology. You've heard me say that numerous times when it comes to oceanography. And we see that. So this is a little bit of an orientation for the currents here. Now, let's take a look at this figure. So there's an awful lot happening in this figure. This is extremely diagrammatic, and the vertical scale is not to scale. Because this is supposed to represent, some 5,000 meters of depth, the light levels would be just a tiny, tiny fraction up here. So bear in mind, this is not to scale. This is just to show you some things that takes place in the ocean. First of all, okay, this represents the convergence zone, where you pile up water in the middle and it goes down, and it brings stuff down. So you've got some cycling of iron. Fe is iron, and these green little, supposed to represent spheres, whatever. That's supposed to be the phytoplankton. Okay? You got some nitrogen being cycled. You got some carbon being cycled. This is all part of the biological pump, where you pump fixated carbon, fixated nitrogen down to death. There might be some other actions as you go down the depth, deeper organisms work on it, whatever, and some of it gets recycled, reintroduced to shallower layers. So you have NO3 here, which is the nitrate. DIC is dissolved inorganic carbon. And NDL is like the nitrogen dissolved layer. And this is the NRL, the nitrogen remineralized layer. More on that in a bit. Now, if we come over to this side here, okay, you see here, it looks yellowish, and then it looks whitish. This is supposed to indicate light levels. In other words, the light is getting dimmer and dimmer as you go down in depth, but the light is very closely tracking temperature. And if you have a well-mixed layer, then the temperature, instead of gradually going up to the surface like that, you get a well-mixed layer here, so you would get some potential mixing within this well-mixed layer. So this is basically uniform temperature to the point where it then starts decreasing. DFE is dissolved iron. Iron is a micronutrient necessary for phytoplanktons. Okay? And that appears to be this bluish line here. NPP is net primary productivity. That's this dark blue. No surprising, it decreases with depth. And this light purple, which closely tracks primary productivity is your nitrogen fixation. So dissolved layers probably means where it is available. Remineralized layer is where it becomes incorporated into tissues. Now look at this blue line here. Okay. You see how this is for chlorophyll A. That's what the CHLA represent. This is chlorophyll A. Uniform concentrations. This is where you're going to get your productivity. And then what happens? Bang. We see it takes a sharp turn and then a sharp decrease. This is the layer they were referring to as being rich in nutrients, but having a hard time getting it up into, you need mechanisms to mix this up into better lit layers. So you have a higher nutrient concentration here, and then here, even though it's uniform in the mixed layer, and then there's a sharp decrease. This here, where the elbow is, if you will, that's your nutri-cline. This is a sharp change in your nutrient levels. We see a similar thing. This yellowish orangey DIN is dissolved inorganic nitrogen. Okay. Fairly uniform concentration. And then it increases because it's not being utilized. So this is kind of what gives you an idea of what's going on here, and in the oceans. And what they're saying is that we can take the photic zones and divide it into a well-lit but lower concentration of nutrients, right, seen here, and a not so, a dimly lit layer but a higher concentration. So the trick is have mechanisms, physical mechanisms, to take this and mix it up into the well-lit layers to help the phytos. Now, if you add in what I discussed earlier, and you've heard me discuss in other videos, with the increasing stratification, the mechanisms to mix the nutrients into the photic zone for the phytoplankton to utilize, those mechanisms are becoming more and more difficult to achieve due to the increasing stratification. And by the way, okay, I'm doing a quick slam course on the Gyres here. If you want the nitty-gritty detail on atmospheric cells, oceanic gyres, Ekman pumping, Ekman spiral, Ekman upwelling, I did a video called Rotating Systems. Please check it out. I explain it all in gory detail there. I think you'll find it worthwhile and very informative. Okay, so now let's get to the Q&A part of what these researchers were saying. In simple terms, for a non-specialist, what are subtropical gyres and where do they occur? Okay, they're away from the continent. They're basin-wide ocean currents, right, that circulate in a clockwise direction in the northern hemisphere, counterclockwise in the southern hemisphere. They occur in subtropical regions and, right, North-South Pacific, North-South Atlantic, Indian Ocean. Subtropical gyres are formed by winds blowing westward near the equator and eastward at middle latitudes. Right? The trade winds, the westerlies, right? those things. The Earth's rotation causes seawater to move to the right in terms of the wind direction in the northern hemisphere, to the left in the southern hemisphere, creating an anticyclonic circular motion in the upper several hundred meters of subtropical regions. And they include the north-south equatorial current, a swift and narrow poleward western boundary current, Gulf Stream, Kuroshio, called the western intensification. And I've discussed that with you guys before. And eastward mid-latitude current and a weaker, much broader equatorward eastern boundary current. Like here, California current. So the double arrow is supposed to indicate that it's a narrow, fast-flowing current. Single black line is a slower, wider current. Basically, it speeds up and then it slows down, returns and speeds up, and so on. And it's all due to Earth's rotation. Next question is, what are euphotic zones and why are they important to understand and model? Euphotic zones are the upper layers of the ocean ranging from tens to over hundreds of meters thick, where sunlight penetrates for phytoplankton, the basic producers, to do photosynthesis, grow, and so on. We all know what the process of photosynthesis is, okay? But, all right, when these organisms die, right, some of them sink to the deep ocean where they are remineralized back into CO2 and inorganic nutrients. That's part of the biological pump. Because of the ocean stratification, which is when less dense, warmer, and or less salty waters stay above denser, colder, and or saltier waters, deep waters take hundreds to thousands of years to return to the surface. And as the stratification increases, this time frame will also increase. This allows CO2 to be stored over long periods in the deep ocean, reduces atmospheric CO2 concentration, and partially alleviates global warming. Right? Look at that. Right? Allows CO2 to be stored over long periods in the deep ocean, reduces atmospheric CO2 concentration, partially alleviating global warming. If the stratification is increasing in intensity, which it is, density currents do not form. You are not going to get this pumping down to depth. You're not going to get this sequestration to depth. You are not going to hide or sequester that CO2 to depth at all, or a tiny, tiny fraction. That CO2 stays in the upper layers, reducing the pH, but as the water's warm, the CO2 starts to outgas back to the atmosphere, not alleviating global warming. However, the slow water exchange also prevents remineralized nutrients from reaching euphotic zones in many regions, reducing biological productivity. In other words, it's a double-edged sword. Oftentimes, the nutrients stay in deep waters as well. It takes a long time for them to come back up, which is why the Antarctic divergence zone is an important region, because this is part of, you have this massive upwelling from the North Atlantic deep water, eventually getting shallower as its density decreases, so it rises. It's deep water bringing up a load of nutrients, which feeds that whole, it surfaces in the Antarctic divergence zone, and then you get the Antarctic front, big biological productivity, krill, whale, baleen whales, the whole, what's down there. The organisms that are found there. Which is why if the deep water formation slows down or shuts down, you shut off that upwelling, you collapse, you don't bring those nutrients into the Southern Ocean, you're not going to get that Antarctic divergence zone. You're going to collapse the food web down there. In many regions, the photic zone can be characterized into two layers. Right, we know this by now. Right? I've hammered on this throughout this video. The upper euphotic zones are sufficient in light but lack nutrient. The lower euphotic zones are nutrient rich yet limited in light. And that's what this diagram is trying to show here. Rich in nutrients, low light levels, got light levels, but your nutrient levels are less, right? This is less than that. And if you want to, this is measuring the, like we often use chlorophyll A as a way to estimate, phytoplankton. And here's your dissolved inorganic nitrogen, right? Low levels here, higher levels here. With nitrogen fixation and therefore net primary productivity decreasing with depth. And you can see they track close together. So what physical and ecological roles do subtropical gyres play in the ocean systems? They're a critical component of the ocean circulation system that redistributes water, salt, heat, carbon, oxygen, nutrients around the planet. They store a considerable amount of heat and carbon and therefore play an essential role in the functioning of Earth's system, including its climate. Subtropical gyres are also the largest continuous ecosystems on Earth. Their current and water convergence limits nutrients that reach euphotic zones, limiting the growth of organisms. Therefore, subtropical gyres are sometimes referred to as ocean deserts. However, certain microorganisms are well adapted to live in these nutrient-poor regions. For instance, tiny bacterial cells called Prochlorococcus are small enough that they require sufficient nutrients to grow. We sometimes refer to them as microplankton or nanoplankton. Typically, the term is more used that you see like nanoplankton for these microbial groups. Furthermore, a particular group of microbes termed diazotrophs can fix abundant nitrogen gas into a form that allows them to get enough nitrogen. This is unusual because primary producers require nitrogen, but usually, especially true in terrestrial, they're not able to take directly atmospheric nitrogen, in gaseous form, and utilize it straight off. The nitrogen has to be fixed by nitrogen-fixing bacteria, put into a form, nitrates usually, that the plants can then use. Well, we've got this group of microbes that can, just like the terrestrial counterpart, take nitrogen gas directly and fix it. It's widely acknowledged that subtropical gyres serve as the primary regions for marine nitrogen fixation due to the ideal conditions for these diazotrophs. They are warm, sunlit, is abundant in surface waters, and forms of other nitrogen nutrients are extremely low, making them good competitors in the systems. Subtropical gyres cover about 30% of the global ocean and contribute a significant portion of total primary production. Right? Net primary production is the difference between total and respiration. Some studies suggest the oligotrophic subtropical gyres are expanding at an accelerating rate in response to anthropogenically induced climate change. Stressors associated with climate change, such as warming, deoxygenation, ocean acidification, can have profound impacts on the ecosystems in subtropical gyres. All true. So, how do you guys observe and collect data from these places? Well, we use a bunch of stuff. We got ships using instruments that you measure physical properties, temperature, salinity, currents, like flow meters, CTDs, plankton nets. You collect seawater samples to take measurements of the chemical species contained in them. What are the nitrite levels, the nitrate levels, the phosphate levels, and so on and so forth. Right? Now, the oceans are a difficult place to work in. It's huge, it's vast, so it's really difficult to get comprehensive data. So we're now deploying, drones, buoys that send information to a satellite that gets beamed back down to the receiver. And we also use Argo. The Argo network is a very important system that really has increased how much data we've gotten, improved our understanding. So we have a lot of tools that we're now using, and the technology continues to improve and increase. And oftentimes, you have to be systematic. You set out a grid pattern there, and you run along the transects. Depending on how much time and money you've got, you cruise a transect, stopping at prescribed intervals to take measurements, collect data. Granted, it's almost like doing spot checks, and we try to connect the dots, but we do the best we can. So this is why using like time series stations is very important. Here we go. Increasingly, oceanographers are using robotic technologies, floats, gliders, sail drones, wave gliders that do not require research vessels and people working at sea to collect observations. So they are very cost effective. You can also employ or deploy sediment traps several hundred meters below the sea surface for periods of days, months, or year to collect sinking organic particles and evaluate carbon sequestration. Satellites also remotely sense temperature, current, phytoplankton biomass, and other properties, giving us important information. How have past time series studies advanced our understandings of tropical gyres? Time series studies conducted since 1988 in subtropical gyres near Hawaii, in the Pacific, Bermuda, and the Atlantic have advanced our understanding. These time series stations have been regularly surveyed, roughly every month. The studies have revealed higher primary production in the regions than previously thought, challenging the notion of these gyres as ocean deserts. Now that's interesting. It could very well be to the activity of the nanoplankton, the microbes I alluded to earlier. One striking observation from these time series is the unexpected temporal variations in biogeochemical characteristics at timescales from hours to decades. Throughout the spring to fall period, the time series stations near Hawaii and Bermuda experience a regular drawdown of CO2 due to the activity of phytoplankton engaging in photosynthesis. Even when nitrogen was not, nitrogen nutrients was not around. Subsequent studies have further demonstrated that the CO2 drawdown and the ensuing sequestration within these gyres are partly sustained by nitrogen fixation. At decadal timescales, an increase in marine biomass and production near the two stations contradicts suggestion of declining global marine production, warranting further investigation. Well, that certainly is an interesting finding. If that can, if that long-term trend can be further verified. But a lot of the studies that I see that look in the oceans do indicate an overall decline of net primary productivity. So, while this is interesting and might represent a bit of a pushback, overall, from what I'm seeing in the literature, is that the NPP, net primary productivity, is in fact worldwide declining at a considerable, noticeable rate. So, what are some of the unresolved questions? Where additional research, data, modeling, are needed. One important question is if subtropical gyres are actual ocean deserts, if their productivity is as low as what we have traditionally thought. They further reiterate their point that time series measurements near Hawaii suggest a moderate level of productivity, while large spatial variations in productivity seem to exist, meaning it's not consistent within a year or from year to year. Satellites can monitor large areas of subtropical gyres, but current algorithms using satellite still cannot produce consistent, reliable estimates of productivity. Another important question: what's the key mechanisms controlling organic carbon export out of euphotic zones into deeper waters in subtropical gyres? The downwelling in the middle where the convergence zone takes place, I think that's pretty much your main mechanism. So they go on and make a few other points, what have you. But this is just really interesting because if indeed there is some productivity that takes place in the middle of these gyres, and based on what we just saw, it could be a way to draw down CO2. But now the question becomes is what happens to the stratification? What happens to the nutrients? Now the indications are, well, it could still draw down the CO2 even without nitrogen. Very interesting. Now, if that's the case, what is the total productivity? And then how does that compare to global oceanic productivity? And then how does that compare to what other researchers are finding, namely that net primary productivity is decreasing? Is it enough to cancel it? Or is it simply just a little bit of a blip, but that does not really change the overall, what appears to be an overall declining pattern of decreasing net primary productivity? So that's very interesting. Another factor is the warming oceans. The solubility of CO2 decreases. So this drawdown may be hindered by that aspect as well. So this is something interesting, and there's obviously research that needs to continue for some time. And that's the thing with oceanography. It takes, to get a really good handle on things, you need decades of data. And oftentimes, you're trying to get funding for a year or two. Gives us incomplete information. Let's put it that way. So, there you have it. Kind of one of those interesting things to, sit there and chew the fat over. Hope you found this informative. Thank you for your time. If you stuck around to the end of the video, thank you for watching. Be sure to give this a thumbs up, as it really helps the channel. And if you can, please support me either on Patreon and or buy me a coffee. Details in the description box below. Thank you.